All right, today's video is going to be a little bit longer than the last couple. We're going to be throwing out a whole bunch of ideas that we're really going to need to work on in class. But basically what we're going to do is we're going to be transforming data to achieve linearity, which is that regression only works on linear data. So what do we do with nonlinear data? Well, we straighten it, but we manipulate math to straighten the data. Or we manipulate the data with math to make it straight. So what we're going to do here is talk about it. So we're going to mathematically transform the data. We're going to talk about how we do that. Applying a function such as a logarithm or a square root to quantitative variables is called transforming the data. So we would take our data, we'd input it, and then to all the x's or all the y's, we would do something. Take the square root, square it, take the log, something like that. And it'll straighten nonlinear data. And in the old days, they used to do this with logarithmic graph paper. And you'd get graph paper that was the log, and you'd plot it. And nowadays, we'll have technology do a lot of the heavy lifting for us. So we'll do an example in class about a fishing tournament, and where they measure the length of the fish and try and relate it to the weight of the fish. And that's going to use a power model, which is where x is the explanatory variable, y is the response variable, but the relationship is that x is being raised to some power, p. And if we can figure out what that power is, then we can just take the p root of all the response variable and plot the points, and it'll get approximately linear. The problem is, what if you have no idea what power to choose? And we'll do an example in class where the power that we'd want to choose is somewhat obvious. But the problem is that not all curve relationships are described by power relationships. So we have this green, this blue, and this red, and they all look to be fairly similar, especially the red and the green. But if we look at this, the red and the green are completely different functions, and the blue is a logarithmic function, which is a whole nother bit of craziness. So the next thing we're going to talk about is, this is mainly what we're going to do, which is transforming data with logarithms. Is anything that's in an exponential growth or exponential decay, which are very common, things always grow exponentially, is we're going to transform the data by taking the log of it. And so to understand why we do it this way, a lot of times it's useful to remember the rules of logarithms. And I just threw these in here. And the big one is the power property of logarithms. If I have, say, some constant to the x power, and I take the log of it, well, that becomes log x times the log of b. Well, this is going to be a constant, and this will be a variable, and now the data will be linear. Right? So if I had y equals this, but I take the log of all of the data coming out, then we get something very different, which is this logarithm. This makes a lot more sense when we play with it, so let's do one of those. And you're going to need to learn these equations here. And remember that log A and log B are constants.
Staff, please pardon this interruption.
And they are really, oh, excuse me.
Still scheduled for today.
Apologize, I'll pause during the announcements.
The library will be closed after school today for May.
And so what happens is, if we have an equation equals y equals the log, y equals a times b to the x, and you take the log of this side of the data, and that becomes the log of a plus the log of b to the x power, which becomes the log of a plus the log of b times x. Normally you'd write the x out front, but if you look at it, if we do this, this is now a linear line, This is now a linear function because this and this are constants. And so we're going to have to undo that. When we make our predictions, we'll use our regression equation, but that's going to make a prediction of transformed data. So then we have to undo that transformation to get back to our way to doing that. And we're going to practice that here in class. So we will fit a least squared regression line to the transformed data and then move forward. So let's look at an example. Here's the classic example that was in the news actually just this week. I'm sorry, let me make this just a little bit smaller so it fits better. Is 50 years ago, a guy was sketching on a piece of paper. He was working at a small semiconductor place, and he was creating this, and he was looking at the number of semiconductors, integrated unit semiconductors they could put on one chip. And he graphed it on logarithmic graph paper. See, this is the log base 2 of his graph, and he gets more or less what he considers to be pretty straight data for 1959, 1962, 1965, 1966. And so he publishes this paper in 1965, 50 years ago. Well, it turns out the guy was Gordon Moore, one of the founders of the Intel chip corporation, Intel Corp. And he predicted in 1965 that the number of transistors on an integrated circuit would double every 18 months. And this is Moore's Law, and it's famous. And if you were paying tech guy, over the weekend they made a big deal about this. So here are the processors that Intel has created and the year that they created it. And so processors here's the name of the processor. They had the 404, the 808, the 880. You guys might remember Pentiums. And now they have the Xenon and all the other chips. So 486 was a big one, and we can discuss why this is in the class. So a few things. When you enter in yearly data, we do not want to enter in 1971. That jacks our data up some kind of fierce. So we're going to recall this. We'll do years. If you look down here, they'll do years since 1970. So this is 1, this is 2, this is 4, this is 8, this is 29, this is 30. And you can see you plot the data that way. If we plot the data, this is our scatter plot. That is clearly not linear data. There's definitely a pattern, and the pattern is definitely not linear. So what we do is we take the natural log of the transistors. And any log will do. Log base E is what the natural log is. And if we plot that graph, we can see here are the points that he had plotted. He used log base 2. We're using log base E. It doesn't really matter in the original one. But we can see that the data is now approximately linear. It looks pretty good. And so this graph is x natural log of y. How you would do this in your calculator is you would put this in L2, and then in L3 you would ask it to take the natural log of L2, and it would spit out. And then you could plot it very easily, and then you would do the LSRL, and your x list is L1, but your y list is L3. And if we do that, we get this equation. The key here is what's under the hat is the transformed data. And what you'll find is we get a very, very, very linear relationship. You can see the R squared value is 98.98. So it's very straight once we do that. And so that's the kind of data we're doing. Oops, and I meant to erase this. Hold on. So this is what we're going to need to be able to do in class tomorrow. And this is where I think we'll pick it up after the video, which is, this is kind of tricky, but or I can redo it. So how would you make a prediction on this? And I think I'm going to have to go over logs in class to explain this, but I will get through this in class. So this is where we're going to stop for today, but what we'll learn in class is how to do this, and then we would look at the residual plots, and we'll talk a little bit about, but this right here, sorry, this slide, and I'll leave it here for a second, is what we're going to need to get out of this unit by the end of next class. Is you need to be able to do this, so pause this and look through this, and this. So we'll pick it up with that Intel. We'll go right into the Intel example at the start of class, and maybe another example as well.